In this lecture video, we are going to cover sections 5.8 and 5.9 in your books. Section 5.8 talks about satellites and weightlessness. Weightlessness is in quotes. Important that it's in quotes. We'll talk about that in just a second. But it's not actual weightlessness, as you can probably assume. Alright, satellites. The best way that I can explain satellites is as follows. We define a satellite as any object that orbits another planet. So, technically the moon is a satellite of the Earth. The first satellite of the Earth, in fact. All the other satellites that we've put into orbit are technically called artificial satellites. Just a bit of trivia. So how satellites work, here's how I can explain it best. I want you to picture the blue circle is the Earth, and I want you to picture placing some sort of cannon or other, I don't know, something that's going to fire something on top of the Earth, right? And it's quite a large cannon, so we can see it from space, obviously. Actually, you know what? Let me make this bigger as I can. Alright, bigger Earth so I can do a bigger cannon. Perfect cannon. Looks awesome. So if we fire this cannon with a certain velocity, let's say, I don't know, 300 meters per second. That's about the speed of a bullet when it leaves the gun. Then we all know what's going to happen according to projectile motion. This object is going to move with a constant horizontal velocity and fall at the same time. So it'll do something like this. Right, move with a parabola. That wasn't the greatest curve, but you get the idea. Right? What happens if I speed up this cannon? I give it more gunpowder or something like that, so it can fire this object faster. Well, the horizontal velocity that's constant is going to increase. So the object's going to travel further. Right? It's still going to hit the ground. So what I can do is I can continue to increase the velocity of this cannon. And you can probably picture what's going to happen. Eventually what happens is I reach a point where I'm firing the cannon so fast that instead of falling to the Earth, it actually just circles around the Earth. So the best way that I can explain a satellite is it's an object that's falling around the Earth, but it's falling so that as it falls, you can see kind of right here, as it falls, it curves, but also the surface of the Earth curves, and those curves are equal. So it never actually hits the Earth. But you should know that a satellite is continually falling. And what keeps it from hitting the Earth is its horizontal velocity, Vx. So in terms of rocket science, for lack of a better term, your velocity that you have to travel, your horizontal velocity that you have to travel in order to circle the Earth depends on your height. We might do an example problem in class because I think it's fun, to figure out how fast you'd have to move in order to orbit the Earth on its surface. And we'll find that it's some really insanely large number. But as you get higher and higher up away from the Earth, that velocity decreases. So that's one of the reasons why we have to get rockets, well, two reasons why we have to get rockets so high up in order to orbit the Earth. One is there's only so fast we can get a rocket to move and still be able to get it off the ground. Because the more fuel we add, the more mass we add to the rocket, the harder it is to actually escape, get that escape velocity from the Earth's gravitational pull. And two, we have to get above the Earth's atmosphere. Because once we do that, we don't have to worry about air resistance any longer, and it makes things a lot easier. So that's essentially how a satellite works, is it just falls, but it's moving so quickly horizontally that it never actually hits the surface of the Earth, it just curves with it. Example 5.15 in your book goes through what's called a geosynchronous satellite, which is a satellite that stays in one spot above the Earth. These are useful mostly for weather purposes. So you'll see weather satellites, for example, pointed right over the United States. All the weather services in the United States would subscribe to the information that satellite provides, but it's just going to stay above that spot. So the most important thing for that problem, the math is not that hard, I don't think. Let me go ahead and show you how they set this up. This is actually just an FNet problem. Essentially what they're saying here is is that the net force on the satellite equals the mass times the acceleration of the satellite. And what they're going to do is they're going to substitute on both sides. So for the net force, we know the net force pulling this satellite into a circle is going to be from the gravitational force, because if you look at the free body diagram of your satellite, this is it. Only one force, the force of gravity pulling down. It's moving horizontally, but remember, that's a constant velocity, so there's no acceleration in that direction, no force in that direction. Right? So from the free body diagram, Fg is your centripetal force, in other words, your net force. So they'll go ahead on the left side, substitute in our equation for gravity. G m1 m2 over r squared. And on the right side, all they do is they go ahead and label this as the mass of the satellite. So let's say m1 is the mass of the satellite. SAT for satellite. So it would be m1. For acceleration, this is going to be a centripetal acceleration since we're looking at a centripetal force. So they're going to substitute in that equation, v squared over r. The r in both cases is the same. Right? The main thing about this problem that you need to realize is that since it's geosynchronous, its period is going to be equal to the same period as the Earth's, which is 24 hours. Right? And that's important in order to find out the velocity of the satellite, because you're going to go to this equation here, velocity equals 2 pi r over t, period. And that's how you'd solve for your velocity. But the rest of the problem is not that hard. Okay, now about the subject of weightlessness, and I'm going to go ahead and type this out. In your book, they put quotes around it. Weightlessness. And it's important that they do that, because nothing is ever weightless completely. If you look at our equation for gravity, and this is a big thing in modern physics, by the way, and also astronomy. If you look at this equation, it is saying that the force of gravity is infinite, meaning that it doesn't matter if you're on, we don't really know the limits of our universe, but you could be thousands of light years away and still technically you would feel a force of gravity. Now your radius there would be insanely huge, so your force of gravity would be very small. But the point is it extends throughout the entire universe, right? So technically nothing is ever weightless because there's always going to be some force of gravity pulling on another object. But we can experience a feeling of what we call weightlessness in certain situations. So the book gives you an example of a person in an elevator, but I think it's easier to think of a person in a rocket, and also a little bit more applicable to this situation. So let me draw. Pretend this is the cockpit of a rocket. Alan, that's not funny that I said cockpit. And we'll pretend that we have our astronaut. I'll go ahead and draw it like this. Our astronaut, excuse me, in this cockpit. Alright. Also in this cockpit we have a scale. And this scale is attached to a bag of some sort. Make it a blue bag. So the scale's going to give us a reading on the bag. Right. The first thing we're going to look at is when the acceleration of this system is 0. Right, so this is when the rocket is just sitting on the ground. If the acceleration is 0, then the net force on this object has to be 0 as well. So when the object is just sitting on the ground, we look at the free body diagram of the bag on the scale. This is what it looks like. Fg, and there's a tension force. Technically, the tension force is what the scale reads. And this is important when you're answering elevator questions, which you do see some on the AP test. It's always the tension force that the scale reads, if it's a hanging scale. If it's a scale on the ground, like one you stand on, it's actually the normal force that it reads. Okay, so in this case, since our net force is 0, Ft minus Fg has to equal 0. Minus because they're in opposite directions. So in other words, our scale force and our gravitational force are the same. Since the tension force is what the scale reads, we could say our weight is equal to the force of gravity. Right? That's a pretty simple situation. That's when the rocket's just on the launch pad waiting to be launched. Let me get rid of this stuff. Now what we're going to look at is when the rocket is accelerating upwards. So let's say, I don't know exactly, let me look this up real quick. How many G's does a, just so we can get something that's realistic. G-force, rocket launch. Let's see. It says the maximum G's here. Space shuttle. Okay, during launch and re-entry, the space shuttle has about 3 G's max force. So we're going to use that. Right, so in this case, this is when the rocket is launched. So we're going to say acceleration, 3 G's by the way, means 3 times the acceleration of gravity, so 3G, and we're going to say this is upwards because it is launching up. Okay, in this case, the force of gravity on the bag is still going to be the same because the mass of the bag doesn't change. Right, so we're looking at the free body diagram. It's still the same 2 forces, mg or fg, whatever you want to call it, and w. Right. So what we're going to look at is again the net force. This time our acceleration is not equal to 0. So when we set up our net force equation, it has to read like this. It's equal to ma. Right. So we look at the net forces in this situation. We're going to say, let's do w minus mg, since they're in opposite directions, has to equal ma. So the weight of this bag, the tension force in other words, is going to equal ma plus mg. Okay. So now we look right here, we know our acceleration is 3 G's, so the weight of this bag, if I substitute in a 3 here, 3G for A, is going to be the mass of the bag times 3... Hold on. I'm not thinking properly. So let me take this step by step. I don't want to lose you here. So it's going to be 3gm plus mg. I could factor out an m here if I wanted to. So the weight of the bag is going to be equal to m times 3g plus g, which is, in other words, 4g, right? Okay. Yeah. So the weight of the bag is going to be 4 times the acceleration of gravity, right? And it's called 3 G's because it's 3 times more than what you would normally feel, which is 1 G. And some students get confused about the 4G or 4gm compared with 3 G's. Right? So when we're accelerating upwards, our weight increases. So let's look at what happens when we accelerate downwards. This is going to be when the rocket has escaped Earth's atmosphere. It makes its gravity turn and starts orbiting. So it's moving horizontally fast enough around the Earth to where it's falling, which is what we said is happening when an object is, or a satellite's orbiting the Earth. So in this case, our acceleration is going to be equal to g, but this time it's going to be downwards. So once again, we have the same setup. Our net force is no longer 0 since we're accelerating. We have to say it's equal to ma. Right? Still, for a free body diagram, it's going to look a little bit different this time. We're going to have the force of gravity pulling down, but there's actually no tension force anymore. The reason being, I'll show you in a second. Alright, so we're accelerating downwards. Let's go ahead and do this. We'll put weight just to put in the drawing. So we get the same situation as before. W minus mg is equal to ma. Right? So W is equal to mg plus ma. right? W here, since our g is downwards, we're going to make it negative, so our weight is going to be equal to mg plus m times negative g, right? It's downwards. Remember, I mentioned this in class before. Remember, don't let acceleration being equal to negative 9.8 meters per second squared tell you the direction of your force, right? These two forces, this force, I already denoted as negative when I drew it like this and subtracted it here, right? So I'm just going to keep it positive. That's what my drawing tells me to do. So what happens here is the weight is equal to 0. Hopefully you see how this cancels out. This would become negative mg, so mg minus mg is equal to 0. The weight in this case is 0. So this is the feeling of weightlessness that you get, or what the astronauts get when they orbit the Earth, right? But it's important to realize, if we go back to our satellite drawing, they're not weightless. They can't be. If they were weightless, they would just fly off into space in a straight line. But since they're orbiting, they do technically have a weight, because there is a force of gravity pulling them at all times towards the center of the Earth. It's just they don't feel that weight. The best way to picture this is, if I go back to my picture here, all of these objects in this little capsule would be falling at the same exact rate, negative 9.8 meters per second squared. So if this astronaut lets go of a cup, for example, he's drinking out of a cup, he just lets go of the cup, it's going to stay right next to him, because the cup, the bag, the scale, the astronaut, the capsule are all going to fall at the same rate. So from that frame of reference, everything looks stationary because everything's moving in the exact same way. I heard a story. I met the director of NASA last summer when I went to a conference, and I heard a story from him about an astronaut who came back. He was about a week back on Earth, and he had spent a significant amount of time in the International Space Station, like almost a year, maybe longer. And the astronaut was eating dinner with his family. He heard his dog or something make a noise upstairs, and he quickly stood up to check out what the noise was. What he forgot is that he wasn't on the space station anymore, so he had a glass of water or something in his hand. When he stood up, he just let go of the glass, thinking that it would just float right next to him, and of course, that's not what happened. It fell to the ground and shattered. So you'll see videos of astronauts on the space station. They just kind of let things float, because it's not a big deal. You know, everything falls at the same rate, so it doesn't look like they're actually falling. All right, section 5.9 I will go through quickly. Section 5.9 talks about Kepler's laws. And these aren't really tested on the AP test, but it's worth your time to be familiar with them, because they are important. So his first law says that the path of each planet around the sun is an ellipse. So an ellipse, if this is, let me draw the sun first. If this is the sun, an ellipse looks something like this. It's an oval that has two focal points. Actually, it needs to be moved up a little bit. One of those focal points would be the sun, and then the other one is just some focal point. That's it. Right, so every planet moves around the sun in a shape similar to this one. It's actually a little bit flatter. Whoops, it's a little bit flatter on the edges than I can draw it on this screen. It's a little bit more squished. It's like a squished oval. So that's the first law. His second law says, in your book it says each planet moves so that an imaginary line drawn from the sun to the planet sweeps out equal areas in equal periods of time. What this really means is that as you orbit around the sun, planets move quicker when they get towards closer to the sun, and then their speed decreases as they're further away from the sun. And that should make sense if you look at our gravitation equation. The closer you are to the sun means the less radius you have. That means the force of gravity has to go up. If my force goes up, my acceleration increases, so I'm going to change speeds quicker. Right? So if this is v1 and this is v2, Kepler's second law says that v2 is greater than v1. You move faster the closer you are to the sun. And then his third law, it says the ratio of the squares of the periods the time needed for one go around the sun of any two planets revolving around the sun is equal to the ratio of their cubes of the mean distances from the sun. What this is, it looks like this. So for planet 1 and planet 2, this is what the equation says. If you square the ratio of their periods, that will equal the ratio of their radii cubed. That's all it says. I don't remember if I assigned any homework problems using these laws, honestly, but if I did, it was 1 or 2. There's the equation that comes with Kepler's laws. The rest is just using Newton's law of gravitation in conjunction with the period and radii equation. Like I said, it's not on the AP exam at all, but it is useful to know. I think it enhances your understanding of gravitation and circular motion. In terms of the rest of 5.9, there's some example problems that you could look at. I don't think they're super important. It talks about this concept called perturbations, which means little deviations from a normal path. So what Newton saw when he was studying the planets is that every planet deviated from their elliptical path a little bit, and he figured out that it was other planets' gravity causing that. And so that example from the last video when we were talking about planet N, it was because scientists observed that perturbation, that deviation from the normal ellipse, and that was what enabled them to predict where Neptune was and tell scientists to point their telescopes into the sky and stuff and find that new planet. This is also how we found Pluto. So these planets were not found by the naked eye first. They were calculated to exist, and then later on, we pointed a telescope into the sky and found that they did, which is interesting. That's how we find almost everything now. Well, I shouldn't say everything. The Hubble telescope has done a lot in terms of us being able to see distant stars and stuff, but for the most part, planets are calculated and not observed. They are observed later after the calculations are made. The rest of Chapter 5 goes over types of forces, but we already covered that. Those should be in your notes. Remember, it's weak nuclear, strong nuclear, electromagnetic, and gravitational. Those are the types of forces, so it's just important to know those in terms of understanding forces, but once again, I don't think I've ever seen that on the AP exam. Alright, don't forget to go do the questions that are associated with this video. Should be pretty short because we didn't cover too much in this video. And don't forget about your homework. The problems are online, and I will upload pictures of the book since I think a couple of you are still missing it. So no excuses. I'm going to look for it in class that you attended the homework.